Welcome back. We are discussing about wastewater treatment, and in this video we'll be talking about the important parameter in the wastewater treatment, which is nothing but the BOD. And before discussing BOD, we should talk about the DO, dissolved oxygen. In one of the previous videos, we discussed briefly about the significance of DO. It is nothing but the amount of oxygen present in dissolved form in water or wastewater. Its presence in raw water indicates water is relatively pure, whereas value in sewage or wastewater is relatively low as it is quickly consumed by the organic matter in the sewage. Because the biological decomposition is always happening continuously in the sewage, because of which the oxygen content will be reducing. If it is less than 4 milligram per liter, the aquatic species will die. Reduction of DO in freshwater is possible when wastewater or sewage is mixed in raw water sources. So that's why we can take it as an indication. When freshwater DO is measured, if it is lesser, then definitely we can identify that when some wastewater or sewage is mixed in that surface water bodies. It's an important parameter to determine BOD of the sample. So this is a DO bottle. This we normally notice in the laboratory. How we are going to determine this DO? This is called Winkler method. Oxygen in the water sample oxidized to iodide ion to iodine quantitatively. For that, the amount of iodine generated is then determined by titration with standard thiosulfate solution. The endpoint is determined by using starch as a visual indicator. The amount of oxygen can then be computed as 1 mole of oxygen reacts with 4 moles of thiosulfate. Prior to the analysis, the sample is acidified to pH 1 to 2.5 using concentrated H2SO4. At the time of sampling, DO is fixed by the addition of manganese chloride, resulting in a brown precipitate of manganic hydroxide. Add sodium iodate, sodium hydroxide solution to it. And when this entire contents in the bottle are now titrated with standard thiosulfate solution to make the solution colorless to the brown color. Amount of standard thiosulfate, sodium thiosulfate solution, whatever we obtain in the titration, that is used to compute the DO present in the water sample or wastewater sample. So now the most important parameter is the BOD. BOD is nothing but the biochemical oxygen demand. As name suggests, it defines that amount of oxygen required to biologically decompose the organic matter in the sewage. So the amount of oxygen required to decompose, that means how much of amount of oxygen is consumed. How you are going to find out that? By knowing the initial DO and knowing the DO final. The difference of this is nothing but the BOD. When we are going to do this test, we should keep the sample under standard temperatures for a specific period of time. These standard temperatures are called incubation temperatures. For that, we are going to use an incubator, BOD incubator. So this is a BOD incubator where we can fix the temperature of the contents by using some control device. So we are having a standard temperature followed here is a 20 centigrade for 5 days. So we have to keep a sample in this at 20 centigrade for 5 days. What is the initial DO before we put here inside? And what is the final DO after 5 days of incubation at 20 centigrade? We are going to calculate using the Winkler method discussed just previously. And then the difference of this is going to give you the BOD. And sometimes we also go for the dilution factor. Why you are going to do that? When the sample is diluted, we are going to apply dilution factor. How total volume of the solution divided by volume of sample. So when you're diluting, we are going to use a fully aerated water. because we are going to supply full amount of oxygen for complete decomposition in the sample. For example, you take only 3 ml a sample and you're taking up to 300 ml dilution. Total volume of the sample is 300, actual sample is 3. So dilution factor is equal to total volume of the sample divided by actual volume of the sample, 100. Dilution is also expressed in terms of percentage solution. A 2% solution dilution means 100 divided by 2. 2% means 2 in 100. So dilution factor is 100 by 2. It is 50 dilutions. So BOD, in case of dilution, you can calculate as DO initial minus DO final multiplied by dilution factor. So initial, if you say 7 milligram per liter, final value if you say 4 milligram per liter, we are going to apply a 2% dilution in the sample. And what should be the BOD here? So 7 minus 4 is the reduction of DO, and dilution factor is equal to 100 by 2. So this is equal to 3 into 50, 150 milligram per liter. So this is the BOD bottle, 300 ml bottle that we normally use in the laboratory. And how the procedure is carried out, as mentioned now, incubation period and incubation temperature. And once we apply this incubation period and incubation temperature, we express this in the form of BOD5 at 20 centigrade. BOD5 means BOD test conducted after 5 days at the incubation temperature of 20 centigrade. If it is conducted for other periods or other temperatures, accordingly it should be done. For example, if you are writing BOD3 at 37 centigrade, means 3 days of incubation at a temperature of 37 centigrade. Though this is also followed, but universally adopted procedure and durations are BOD5 at 20 centigrade is the standard incubation time and incubation temperature. Suppose if you say, take another calculation, 7 milligram per liter initial DO, final DO is 4 milligram per liter. So sample of sewage taken is only 5 ml. And how much is the BOD? 5 ml is diluted to 300 ml using your dilution water, which is fully aerated. And sometimes we also supply enough amount of nutrients so that bacteria can grow without any difficulty. So now dilution factor is equal to 300 by 5, which is equal to 60. 7 minus 4 into 60 is equal to 180 milligrams per liter. So now we'll see how to calculate the BOD through in mathematical form. So now this is called as a BOD rate equation. Let LT is the amount of biodegradable organic matter present in sewage at any time T days. The rate of degradation can be expressed as a first order reaction. dL by dt is equal to minus KL. So dL by dt is proportional to L, and because the value you can see here, organic matter remain. Initially, high amount of organic matter is remaining, but as time passes, the organic matter is reducing like this. So it's an exponential reduction. So that's why you are assuming is a first order reaction. dL by dt is proportional to L, and because it is reducing, concentration is reducing, so we are introducing a negative sign here. It indicates the concentration is reducing, or organic matter remaining is reducing. So separation of the same terminology or same terms here, dl by L is equal to minus K into dt. Integrating, so this is T is equal to 0, so T is equal to T. When T is equal to 0, L is equal to L naught. When T is equal to T, L is equal to LT. Within these two boundaries, we are going to do this calculations. So ln of LT minus ln of L naught is equal to, so ln of LT by L naught as per logarithmic rules is equal to minus KT. So this is ln, nothing but logarithm, natural logarithms. So therefore, This is LT by L naught is equal to the base to the E, so E to the power of minus KT, where K is nothing but a decay constant or deoxygenation constant. Why deoxygenation? Because oxygen is reducing in the oxidation processes which is happening in the biological decomposition. So LT is equal to cross multiplying L naught into E to the power of minus KT. So BOD is what we are saying at the end of some fixed period of time, how much of oxygen is reduced. So at the end of T, this is the value. Initially is this. How much of oxygen is consumed in this period? L naught minus LT. That is nothing but your BOD. So your YT is equal to, we represent by BOD in Y, and T stands for the time period. L naught minus LT. So L naught minus L naught into e to the power of minus KT. L naught is separated out, 1 minus e to the power of minus KT, where L naught is initial BOD, and T, if I say infinite, suppose infinite time, you can see it is never reaching here. So when T is infinite and put T is infinite here, then ultimately what will happen? Y infinite is equal to L naught. This entire thing becomes a zero. So L naught into 1, that is equal to L naught. So Y infinite is equal to L naught. What is Y infinite? This is BOD at infinite time, or ultimate BOD. So ultimate BOD is equal to initial BOD, which is equal to L naught. And K is nothing but KD as a deoxygenation constant. And we are writing as 0.23 per day at 20 centigrade. This is also can be experimentally determined, and the standard value we are using for all the practical calculations. And this KD again varies with reference to temperature. And at any other temperature other than 20, we can calculate K or KD as KD at any temperature T is equal to KD at 20 centigrade into 1.047 or to the power of T minus 20. Sometimes in textbooks, it is given in terms of base 10 KD. So KD at base 10 is equal to conversion, natural logarithms to common logarithms. KD at the base E divided by 2.303. And similarly, this equation number 4 can be written as YT is equal to L naught into 10 to the power of minus KDT. For example, when KD is equal to 0.23 as given here for 20 centigrade at the base E, and this value with reference to base 10 we are going to have as 0.23 divided by 2.03 is equal to 0.1 under base 10. Whenever we are mentioning about KD value, standard value, we should clearly mention under what basis. This is base 10 or base E, and at what temperature. And what are the importance of this? You can see here the BOD value should be less than 30 milligram per liter when you are to dispose the wastewater in surface waters, and it should be less than 350 milligram per liter when you're disposing into the municipal sewers, and should be less than 100 milligram per liter when you dispose it for on land and marine disposal. Now we'll try to look at these two graphs. So now you can see here this the downward graph is nothing but BOD remaining at any time. So BOD remaining and BOD available is this graph, BOD exerted. Ultimate BOD is this. So you can see from these graphs how they are varying, at time T is equal to 5 days. So how much is the ultimate BOD, which is around 60 to 70%, which is usually around 68% of the BOD file. So this is how we try to look at this particular thing. BOD remaining, if you look at from this graph, at 20 days of time, the amount of BOD remaining is very, very small, and the amount of oxygen exerted, you can see, is almost reaching to the 100%. Okay, so this is what it is. So that means by the end of 20 days, the BOD exerted is almost complete, and we can assume that a 20-day the BOD is a complete process. But actually speaking, this organic matter is having two types of organic matters: carbon-based organic matter, nitrogen-based organic matter. And what are we are talking is only the carbon-based organic matter decomposition, which we are talking through the BOD test. In the nitrogen-based organic matter decomposition, so that is again also there. So now you see this particular graph I'm taking here, the second graph, amount of oxygen exerted 99%, and this is there. And the second stage of oxygen requirement will start after that. That is what you're calling as a nitrogenous BOD or second stage BOD. This again starts after 20 days of time. But usually, when we talk about BOD, we only talk about the first stage BOD, which is nothing but carbonaceous BOD, and that too we will be mainly concentrating on 5-day BOD. That we can extrapolate to calculate BOD at any given time, provided we know the deoxygenation constant at a given temperature. So how to do that? We'll take up some small problems that will be easily understood. So what is more important to understand at this stage is there is a carbonaceous BOD, there is a nitrogenous BOD. We'll be mainly focusing about carbonaceous BOD. And from the first graph, what we understand is at the end of 20 days, most of the oxygen is exerted, around 99%. Very small amount of BOD is remaining.